Log on, tune in, find out. Another good idea from Cambridge.
This polynomials, if there were three parts, this is the polynomial part. And essentially the story is the story of the Weil character formula. So let me, this lives in the world of symmetric functions. And of course we begin with the setup which by now should look a bit familiar. So dual Z vector spaces which are paired by a form which I denote with angle brackets. And W naught is a finite subgroup of GLHZ, so it has integer entries this time. So everything is a Weil group today. Everything is a Z reflection group, not a C reflection group. Is a finite subgroup generated by reflections. So I should say that one of my dreams is that someday we will be able to do today's story for non-Weil groups. But at the moment I have no idea how to do that. Well, that's a little bit of a lie. Okay, so W naught acts on the group algebra of the lattice. So the group algebra of HZ. So let me call it KT check of a point. So this is a fancy notation for the group algebra of this lattice. So it's spanned by basis elements y to the lambda check with product given by the addition in the lattice in the vector space, and action given by just the action on the lattice. Okay, so that's my ring of polynomials. That's what I think of as polynomials. It's really Laurent polynomials, as we saw last time, but for me, that's where the polynomials live. Okay, so the algebra of symmetric functions is then KT check of a point W naught. So this is all of those polynomials such that W acts trivially on F for all W. So these are the W naught invariants in the polynomials. That's the algebra of symmetric functions. Clearly, if I multiply an invariant times an invariant, then I get another invariant. So it's an algebra. Say it. No. So I'm defining now, this is not a semi-direct product. This is not the affine Weil group. This is just an action of W naught on polynomials. Yeah. It's a good point because the affine Weil group will appear in a bit. But here I don't have an affine Weil group. Yes. Okay. So then there's another space which is sometimes called alternating symmetric functions or skew symmetric functions. So these are all of those polynomials on which W acts by the determinant representation. So of course The trivial representation is a one-dimensional representation of W, but there's another one, which is the determinant. If you take the determinant of a matrix, you get a number. That's another one-dimensional representation of W. And the Weyl character formula is essentially the following statement, that this is a free KT check point mod W naught module of rank 1. Okay? So skew symmetric functions is not an algebra. If you multiply two skew symmetric things, it's not skew symmetric. However, if you take a skew symmetric thing and multiply it times an invariant, it's still skew symmetric. So it's a module for these symmetric functions. And it turns out to be a free module of rank 1. So let's start to study this. I'll draw a picture in a moment. But so let me write it this way. KT symmetric functions and skew symmetric functions. It's easy to construct bases of these vector spaces, have bases, so m lambda check will denote the monomial symmetric function. So here my notation is that pi 0 is just the symmetrizer. So view it as an element of the group algebra of W naught. If I take a monomial and symmetrize it, I get a symmetric function. Well, it's the most naive thing one can do, right? And of course, if I take a monomial and skew symmetrize it, so epsilon 0 is the sum over W in W naught of the determinant inverse W. So I skew symmetrize a monomial, and I get a skew symmetric function. Okay. So the only question is, can you pick out a basis? And the answer is, I didn't leave my, is a set P plus, and I drew a picture, so it's just easier to draw a picture here. So this is my Weyl group and my lattice. So that's a Z lattice, and let's see, what color should we use here? So if I symmetrize, if I make something symmetric, well then it's just a sum over the orbit. So the linearly independent ones will be representatives of the orbits. And these points, which are in this chamber, these are representatives of the W naught orbits on this space. So P plus, we could call it that. That's HZ mod W naught. Those are representatives of the W naught orbits. Now, let's think about skew symmetrizing. Well, skew symmetrizing, the same thing happens. You get a sum over the orbit. But what happens is that these guys on the walls, they turn out to be 0. So all that's left after you skew symmetrize is the ones that are not on the walls. Can you see that orange? A little bit. Good enough. And it's somehow clear from the picture that the non-orange, the purple circle dots, if I push them up by rho, I get the orange dots. So this point is called rho check. And if you take a purple circle and add rho check, it becomes an orange dot. So I can actually index them by the same lambda checks, but I should add rho check to indicate that I've pushed into the orange. All right, so that's, if you ever wondered what rho is, that's what rho is. It's the generator of that orange cone. Okay, great. So now we can draw the picture. Maybe I'll shut this off and and draw the picture of Weil's character formula here. So I have symmetric functions, and I have skew symmetric functions, and I have a map. So being a free module of rank 1 says that there's a generator here, which is a row check, and everything in here is obtained by multiplying that generator by a symmetric function, and that's an isomorphism. That's what free module of rank 1 is. So let's see what that is. So this is the naive basis. That's the most naive thing I can do. All right. Let me write here. So m lambda check is the monomial symmetric function. If you read MacDonald's book on symmetric functions, that's where I get my terminology from. And so let's call that the naive basis, because that's the one you would first write down. And over here, we have another naive basis. Okay, but if you take this naive basis and pull it back across this isomorphism, that's a non-naive basis of symmetric functions. So S lambda check is the Weil character, or the Schur function. So if you ever wondered how would you naturally come up with Weil characters, well, you just take the naive basis over here and pull it back. It's obvious. Okay, now this A row check, this generator of skew symmetric functions as a free module, as a rank 1 module. So A row check, this is the Weil denominator, or it's sometimes called the van der Waals. All right, so you can write formulas for these things, but I don't need to write formulas. It's just what they are. Okay, so I need now just to make one remark about this picture, and that is that kt check of a point w naught. So what's the theorem of Weil? It says that this is the same as kg check of a point, which is the Grothendieck group of g check modules. So G check is the corresponding algebraic group that you would get, whose G check is the algebraic group whose Weil group is W naught and whose lattice is Hz, if you construct it the way that Hz star, I guess, if you construct it the way that I did day before yesterday. And so, in fact, this ring here is the representation ring of G check. And more, what Weil says is that the S lambda check are the images or the classes of the simple G check modules. All right, so if you like, you can think of it, suppose I just wrote down this ring. What I've just done is I've categorified it and its G check modules, and I've identified the simple objects, all right, in the Grothendieck group. Okay, so that's the basic story. Now we need to go to our new favorite object, and I have to remind you about the double affine Hecke algebra, which is H tilde. So H tilde, I'm not going to write all the relations down, but I'm just going to give you enough to work with it for today. This is actually how we work with it anyway, so we don't need all those relations. So it has a basis, which is q to the k on e. E is that number over there. It's 1 most of the time. X to the mu, t w, y to the lambda check. So k is an integer, w is in w naught, mu is in the first lattice, and lambda check is in the other lattice. And it looks like it looks like a semi-direct product, a central extension of a semi-direct product of W naught with a Heisenberg group. Okay, so that's our concept. Inside of this, there's a subalgebra, which is the affine Hecke algebra. Oh, let me write this slightly better. It has basis, this set. Okay, the affine Hecke algebra is the span of x to the mu GW, mu in Hz star W in W naught. And inside of there is the finite Iwahoori Hecke algebra. These are the ones that have been appearing quite a lot in Meinolf Gex talks. And so let me remind you a few of the relations which help you to think about this. So this element q to the 1 on e is in the center, so it commutes with everything. So you could view it as a constant or a parameter. Of course, the lattice part is not deformed. The lattice part is just a lattice. Both lattices are just lattices inside the double affine Hecke algebra. Okay. But this finite part is deformed. So let's but H0 is generated by some symbols which we'll call T1 up to Tn, and relations which I'll use today. Ti squared is t to the half minus t to the minus a half, ti plus 1, and ti, tj, ti is tj, ti, tj, where you have mij factors on each side, and pi over mij is the angle between the hyperplanes for those corresponding reflections. So in other words, this guy looks just like W naught. It has a Coxeter representation, except that the TIs don't square to 1. The TIs have eigenvalues. Maybe I write that. So TI has eigenvalues in any representation, t to the half and negative t to the minus half. So instead of being a reflection and having eigenvalues 1 and minus 1, it has eigenvalues t to the half and negative t to the minus half. Okay, so that's, I think, all we need to know about the double affine Hecke algebra for today. T is another parameter. View it as another parameter. It commutes with everything. Yeah. Okay. Right. So now the subalgebra H check. So this affine Hecke algebra has a one-dimensional trivial module, has so let me write here, unique one-dimensional module. Let me call it span of a single vector, which I call big 1, boldface 1, with ti1 equal to t to the half. Okay, so this, I just said that ti has eigenvalues t to the half and negative t to the minus a half. If I'm choosing a one-dimensional module, I've got to choose one of these eigenvalues. Let's choose this t to the half. And then I'm saying that there's a unique lift to a one-dimensional module when I go to the affine Hecke algebra. So in fact, the action, if I want a one-dimensional module, the action of the x's is forced. All right? There's a horrible formula, but I don't want to write it down. It's just forced. Okay. So now the polynomial representation. So if you, I'm not expecting you to remember anything that we did yesterday, but if you do, there's an analogy here. I did exactly the same thing. I took a one-dimensional module, and then from that I built a polynomial representation of the next object is the induced module. And the way you build it is you induce the trivial module up, and that's something which we could call like this. And let's think about what happens. Well, all the x's and all the tw's get killed by 1. All right, that's a one-dimensional module. So all that's left is the is the y's. So I would like to write this. I'm thinking of q as a parameter now. I would like to write this as kt check of a point times 1. Okay? So that space, those functions there are inside my double affine Hecke algebra, or they're trying to, or at least a module for my double affine. And not just any module. My favorite module for the double affine Hecke algebra has that world in it. Okay. So now let's define. So now we have to make symmetric functions. These are not symmetric, so we have to make the quantized version of symmetric functions. So let's define two capital 1, 0 and capital epsilon 0 in H0 by, so I want 1, 0 ti to be t to the half 1, 0, and epsilon 0, capital epsilon 0 ti to be negative t to the minus a half capital epsilon. All right, so again, we can write down explicit formulas for those. This is a finite dimensional algebra with basis indexed by the elements of the Weyl group. I can write down the formulas if I wish, but I don't wish to. It just looks messy. But they're completely determined they're determined up to a constant by these conditions. This is the minimal idempotent corresponding to the trivial representation, and this is the minimal idempotent corresponding to the sign representation, or the determinant. Okay. So now we can build symmetric functions. So now I'm going to state a lot of things which are not quite trivial, but are not difficult. So if you like, we can call them exercises. And you can. So the first statement is that let's take so h tilde 1. So I just said that h tilde 1, actually, let me write this a little bit to the left here. I just said that h tilde 1 is polynomials times 1. That's my polynomial representation. Now let's take polynomials and symmetrize them. What should you get? Well, you should get symmetric polynomials, right? Except that everything is a little bit quantized now. There's a t in all this. So it's actually a little bit amazing. Of course, there's a map here, which is just multiplication map. Let me put the 1. Okay, so now I have an analog of symmetric polynomials, or more than an analog. I have symmetric polynomials sitting inside of Daha. Right? Sitting in Daha is the double affine Hecke algebra. Sorry, when I say Daha, I mean Okay. All right, so now I need to define the Magdano polynomials. So the non-symmetric Magdano polynomials, so polynomials. So I'll call those E lambda check. Sometimes I'll be careful and denote that Q and T are appearing in these. So Q and T are appearing all over the place in these polynomials. These are polynomials, so they should be living on the left-hand side of this diagram, are given by two properties. So the most important property is that their eigenfunctions, E lambda check is an eigenvector for all the x mu's. So here we clearly have a left H tilde module. And x mu is inside of H tilde. So x mu acts on this. And the x mu's, they all commute with each other. Now, whenever you have a big family of commuting operators, you call them UC-Smurfy elements, and you try to diagonalize them. Right? So, in fact, these are the UC-Smurfy elements. In type GLN, they're exactly the UC-Smurfy elements. So, okay, so I try to find eigenvectors. This is exactly what Sasha Kleshev was doing yesterday for all these x mu's. And the second thing is that I'm going to normalize it so that this is y to the lambda check plus lower stuff. If you think about the monomials indexed by my lattice, if you think about the monomials indexed by these dots, then lower stuff means that it's inside the convex hull of the lambda orbit. All right, so if you take the W naught orbit of lambda, take, that looks like a big hexagon or octagon, take the interior of that, that's what I mean by lower stuff. All right. So that's the non-symmetric Magdano polynomial. Those are not the original Magdano polynomials. Those were defined somewhat later than the first Magdano polynomials. So sometimes there's a confusion about what a Magdano polynomial is. The original Magdano polynomials are the symmetric ones. Polynomials. So those are called P lambda check, and if I'm being careful to denote their dependence on Q and T, I'll write P lambda check QT. Those are now symmetric functions and are given by, now the simplest way to get this is that this is the image of E lambda check under that map. All right, so the E lambda checks are sitting here on the left-hand side. If I take E lambda check and push it there, it's a symmetric Magdano polynomial. So it's exactly the symmetric version. And of course, I only need to consider these for lambda and dominant weights in the representatives, because it's symmetric functions. Now let's define, if you want to do Weil character formula, you need this side of the story. But that's now easy to define. Define A lambda check plus rho check, which, again, if I want to have it clearly depend on Q, then I will, so these are polynomials, by, so A lambda check plus rho check acting on 1 is epsilon 0 of E lambda check plus rho check 1. So Again, you should think of it like this naive basis over here. This naive basis, this was, I took a monomial and symmetrized it. And this naive basis over here is that I took a monomial, skew symmetrized it, and symmetrized it over here. Okay. And here I'm doing exactly the same thing. I took a monomial, a monomial, and symmetrized it. And here I took a magdanomial. You should think of we know now that we should think of these as monomials, except of course they're not. They're horrible combinations of y's. And skew symmetrize it. All right. Warning. There's a warning here. It is not true that if you take polynomials and skew symmetrize it, that is not skew symmetric polynomials times 1. Okay, so that here I said if you symmetrize Daha polynomials, you really get symmetric polynomials. But if you symmetrize Daha polynomials, you don't get skew symmetric polynomials. You get some Daha skewed things. Okay, great. So I think. That's right. That's exactly right. Okay. Good. Now we can draw my big picture. This is my favorite picture. One at least. One of my big motivations is the following picture. Okay, so I would take symmetric polynomials. So that's kt check of a point w naught 1. And Daha skew symmetric polynomials. And I will define a map from 1 to the other. So let me put the qt in here. Okay, so I'm thinking of a Daha polynomial as a symmetric polynomial times 1. So this is a map. And this is a non-trivial statement, although it's not nearly as hard as it used to be, is an isomorphism. In some sense, we've just said that there's a Weil character formula in the Magdano polynomial world. We've said that there's one element, one generator, a row check. If you multiply that by symmetric functions, you get this thing. This is a free module of rank 1 over that. And that's an important algebra, we think anyway. We think it's okay, so these guys are the naive basis. Because, so we'll put here quotes naive basis. Because if we just got them by symmetrizing a McDonald monomial, all right? And these guys over here are the naive basis over here, because again we got them by symmetrizing this thing. So again, let me write here naive. Okay, so the next theorem is, what do we get when we pull this back? All right. Whatever we get, right, this Magdano polynomial, notice, this is one of the confusing things when you start with Magdano polynomials. This Magdano polynomial is not the analog of a Weil character. Okay. This Magdano polynomial is the analog of a monomial symmetric function. It's the naive basis. So when you take the naive basis on the other side and pull it back, what do you get? you get P lambda check of Q QT1. Right, so somehow this is for me an amazing theorem. Okay, I think we'll now move to here. I don't actually know. Probably it is. I mean, most things of the story are in Cherednik somewhere. I learned it from McDonald, so I don't really know, but I'm. That's right. That's right. So this formula is very related to what you call shift, or Erik Opnam's shift operator, and so it was in the air in many ways, and I'm sure that Cherednik had it in some version. But okay. All right. So now my next favorite picture in life is the same picture, but at q equal to 0. Okay. So at q equal to 0, we're going to write the same picture over. So I start with 1, 0. H, well, let's write H tilde, 1, 0. And let's put F1 here. So this is, of course, KT check of a point W naught 1. And let's put P lambda check of 0 T1. And let's put P lambda check of 0, 0, 1. And let's put here epsilon 0, H tilde 1. And here A row check of 0, T1. F1, and a lambda check plus row check of 0 T1. Okay. Now maybe I should use a different color because I'm going to start to decorate this. So the first thing that happens at q equal to 0 is you can remove this tilde. All right, so I remove this tilde, and so this is where the affine Hecke algebra is the span of TW y to the lambda check W and W naught lambda check H. Okay, so I can remove that tilde. Should I erase it or should I cross it out in yellow? Which do you prefer? I don't know. Nobody has an opinion. So I would like to erase it because for me it feels better. All right. So the next thing that we can do is this 1 on the right can be changed to 1, 0. All right. And it doesn't change anything. So I'm making now changes in notation, but not changes in any of the spaces that we're talking about. Okay? So the 1, 0 is enough in the affine Hecke algebra to do the job that 1 was doing in Daha. So it's okay once you put q equal to 0. 1, 0. Okay, so again, I mean, still, this is an isomorphism. And I need to say something here. So this this object P lambda check 0 T was well studied before. So P lambda check 0 T is called the McDonald spherical function. or the Hall-Littlewood polynomial. So if Hall-Littlewood polynomials ever entered in your life or ever will enter in your life, that's what they are. And certainly there's a very extensive, beautiful work on this by MacDonald in 1971. So everything you would like to know about MacDonald polynomials, about spherical functions on p-adic groups. So this is a spherical function on a p-adic group. In general type is in this thing in 71. So the left-hand side of this picture, so far is in MacDonald in 1971. Okay, the next statement is that this thing is S lambda check 1, 0. This is due to Lustig. This is S lambda check. Right? This is the Weil character. Now, what did we do? We took the Weil denominator, we took skew symmetric functions, we quantized them, we put a t in, we got skew Hecke polynomials. And Lustig says if you pull back the naive basis in skew Hecke polynomials, you get the usual Weil character. So now we're confused about whether Weil characters have to do with Weil or with Lustig. I mean, which one is really the core of the Weil character? Well, so that's the usual thing. So that's the theorem of Lustig. Okay. Now, maybe maybe it should be clear at this point that this picture over here that started with Weil is the same picture as on the upper left corner at q equal to 0 and t equal to 1. Okay, so if you specialize q to 0 to get this picture, and then t to 1, this becomes exactly the Weil story. Exactly what we had in mind. Okay, great. How are we doing? Let me make some remarks. So the first remark is, so when q is not 0, the center of the affine of the Daha is trivial. In other words, it's i.e. the center is polynomials in q to the plus or minus 1 over e. Okay, so whether you think of that as a number or as a variable, the center is trivial. It's what you think it is. But however, at q not equal to 0, at q equal to 0, which is somehow this picture now, the center is big. Is big, and it contains in particular the center of H, all right, and the center of H is yeah, just when I have these idempotents killing things around, yeah. They're not the same, no. So this is symmetric functions. So I said here, is the Weil character a Weil story or a Lustig story? I mean, fundamentally, did it come from Weil or did it come from Lustig? Is there somehow, does the Weil character somehow know about T? But Bernstein, so this is a theorem of Bernstein, says, well, is symmetric functions what Weil thought it was, or does symmetric functions really have to do with Hecke algebras? I mean, is symmetric functions really at its core being the center of the Hecke algebra, of the affine Hecke algebra. That's what Bernstein is. Okay, so that's a beautiful statement. The next remark we have to make is so if I put one more, maybe I should put one more equality here, which is center of H10, and label this by Bernstein. Okay, and then I can label this by Lustig. So now we have another equality there. So the map, so we can view this map. So you think of taking, well, let me write it this way. Suppose I take a monomial. Actually, I should put that. That's another fact from MacDonald, is that if you take the ordinary monomial and symmetrize it, that's the spherical function. And here, if you take the ordinary monomial and symmetrize it, skew-symmetrize it, that's this Lustig element, this naive basis. Okay. So from when we put q equal to 0, the MacDonald monomials turned into ordinary monomials already. Okay, so this map, of course, this is, I wrote equals. In fact, it's equals, but we can think of it as a map from polynomials to symmetric functions. I sort of think of this map as, this is called the Satake isomorphism. All right, so it says that this Hecke algebra is isomorphic to symmetric functions. That's called the Satake isomorphism. So if you ever are studying anything related to groups over local fields, you will hit this Satake isomorphism, and this is what it says. Okay, so that thing, so now I need to make two comments. Let's call this remark, so let's call that remark 2, and let's start with remark 3. So the next remark is that H is the Grothendieck ring. So I'm viewing here under convolution of I equivariant. So this is, let me say it. Let me write it first, and then we'll perverse sheaves on the affine flag variety. So I'm using exactly the notation that I had 2 days ago. So G mod I is equal to the affine flag variety. Did you talk about convolution at all, Paramount? No. So, I mean, we did it 2 days ago. We multiplied the double cosets. That's what convolution is. Just put it into the perverse sheaf world, and that's convolution. All right, so this object down here is actually an algebra of perverse sheaves. All right? So let's continue with the remarks here. I think I can erase this now. And let's, the spherical Hecke, so this is sometimes called the spherical Hecke algebra. Hecke algebra. Is isomorphic to the Grothendieck ring of K equivariant perverse sheaves on G mod K, where G mod K is the loop Grassmannian. Okay, so it means that in this picture, right here I have, I don't know what we want to call it. Here I have perverse sheaves on G mod K. And here I have okay, so there are a lot of equalities here. Okay, let's call that the K group of perverse sheaves on G mod K. And here I have G check modules. And I really want check here and not non-check, which I want non-check here. This observation of Lustig was what kicked off geometric language. So this is the source. I can write it here. This is the source observation is the source of geometric language. And it has been studied, it is studied intensely. However, I've always felt that this side of the story, with perverse sheaves on G mod K and G check modules, has really been studied intensely. But this side of the story hasn't been studied that much. It pops up every once in a while, you see it. But I think that studying this side geometrically would be, there's a lot of gold here, because this is the naive basis on this side. Okay, so I just said that this is the naive basis. Let me point out that this basis that we got, so this is now a basis of K equivariant perverse sheaves on the loop Grassmannian, is that, or it's a basis of the spherical Heck algebra. So which basis is it? It's the Kazan-Lustig basis. So again, this is due to Lustig basis of, okay, so those vowel characters, you thought they were vowel characters, but in fact, that means that this thing is the image. Now, Pramod, you can check if I got my notation right, of this was the double coset that appeared 2 days ago in my double coset decomposition. If I take that stratum, I take the trivial local system, I take the IC sheaf of that, I take its image in this spherical Heck algebra, that's the short function. That's the vowel character. All right. Okay. So I hope that with these remarks, I have convinced you that there is some geometry here. Okay. I have not made any comment about the geometry there. But hopefully I gave you a feeling, at least, that this picture comes from that picture. So maybe we should stop there.